everybody. I think that now it becomes to be more and more people. Maybe we will still wait for a minute, but start very soon. So just to introduce quickly, welcome back to this COMSOC video seminar. There was a time that we didn't see each other, all of you. So it's a great pleasure, and it's also a great pleasure for me to be part now of this organization committee. So it's a real pleasure. And today I think it will be very exciting because we received two researchers. So Hadi Hosseini and Martin Bullinger, who will talk about different interesting topics. So Hadi Hosseini will talk about fair division typically, and Martin Bullinger about matching markets. Should I still wait for 2 minutes, Dominique? No? Should we start? Okay, so Hadi Hosseini is an assistant professor at Penn State University, and he will talk about distributed mixed items fairly, a lexicographic excursion today. And please, you can share your slides maybe and start soon.
Okay, let me see. Just let me know if you see my slides. And
yeah, that's perfect. And like usual for the audience, if you have questions, you can write them in the chat by writing capital letters question before your question, and Hadi will answer them at the end. So the stage is yours, Hadi. Thanks.
All right. Thank you very much, Nali, for that introduction. And hello, everybody. Good day. I know there are different parts of the world. So if you're where I am, good morning. And if you're somewhere else, good evening, good afternoon. So as Anali mentioned, my name is Hadi Hosseini. I'm an assistant professor at Penn State. And today I'm going to talk about distributing mixed items fairly. And I'm going to focus on lexicographic preferences. One weird thing is that when you're giving these type of talks, I really don't see any of you guys. So I'm just talking to my computer. So if something comes up or if something goes wrong, please feel free to unmute yourself or leave a comment in the chat section. I think I'll be able to see those. Okay, so before I start, I want to kind of start with thanking my collaborators because I'm not sure if I timed this talk very well. So if I manage not to finish it, at least I have thanked my collaborator because I want to give a lot of credit to them because without them, I would not have been able to present this work. And this talk is not about one single work, it's about series of works, but I'm going to focus on a few of the findings that we have, giving you like an overview of fair division under lexicographic preferences. Okay, so the overview of the contributions, I'm going to talk about non-existence of EFX under mixture of when we are allocating mixture of goods and chores. I'm going to talk about its computational complexity very briefly, and then I'm going to talk about some of the special cases for which we can actually solve this problem. And then I kind of go further and talk about some of the other challenges. And I have a bunch of open problems that I'm going to kind of throw it at you. And hopefully somebody would be interested in kind of brainstorming with us. Okay, so let's start with defining what lexicographic preferences are. I am assuming most of you are familiar what these are, but I'm just going to give you a very brief introduction. So these are preferences that are generally known to be strongly monotonic and responsive. It's a subdomain of additive preferences, and it actually allows us to have succinct representation over various choices. Right? So in this case, I can give you an example. So if you have an agent who says, hey, I like this bundle more than this other bundle, then it means that we can kind of infer that there is an item in that bundle that is liked more than any other item in the other bundles, and so on and so forth. And that way we can actually create a linear ordering. The good thing about lexicographic preferences is that you can have a linear ordering over single items, and then from there you can have an extension over all possible, it will give you a total ordering over all possible bundles. Okay, why do we care about lexicographic preferences? Okay, so here's my 3 thoughts. One is that I'm going to argue that we are often lexicographic beings, which I'm going to call it homo lexicus. Second, I think domain restriction is very common in our field, as you have seen. And I'm going to show examples of how lexicographic preferences have been looked at. And third, this actually reveals a lot of insights about computational and structural aspects of our problem. Okay. So a lot of you have probably heard the term Homo economicus, which was kind of coined by, I think, Adam Smith, John Stuart Mill, and they talked about humans as these rational utility maximizer agents. I want to argue that in most of the situations, I don't want to say in all situations, but in most situations, you're actually more Homo lexicus. And it's easier for us, and one of the reasons is that it's more natural to think about ranked features or ranked items for us rather than having exact weights to compute a utility for any choice. And this is exactly becomes because of the fact that it's just easier for us to think lexicographically when we are making decisions or when we are comparing things. And I'm going to give you examples. If you're purchasing a car, for instance, you start looking at, well, I prefer to have an SUV. And then once I kind of set my mind on having an SUV, I think about whether it should be electric or gas and so on and so forth, right? In hiring faculty, it's actually the hiring faculty season right now in the US. Like for tenure track faculty, we care about research, right? No amount of teaching is going to replace the amount of research that somebody does, right? Same goes to service. When we are assigning TAs, for instance, I really prefer the TAs that I have worked with and they have experience with. So if I get Alice, I don't even care how many other TAs you're going to give me because I've worked with Alice. I know Alice is good. She knows exactly what she's doing. She's very responsive. So even if you give John and Herbert to me, I'm still going to prefer Alice, right? So this is just my preferences. And the same thing goes with assigning tasks or what we call chores. Right, so there are people who don't want to clean the bathrooms, like they would prefer to take the dog out or wash the dishes, but don't do the bathroom. I hate, like myself, I hate you doing the bathroom, cleaning the bathroom. And there are some people who are, let's say they are, what's it called, allergic to dogs, right? So they cannot take the dog, so they would prefer to do anything else other than that. Right? So it's very natural to think about lexicographic preferences in this sense. So that was my number one. Why we care about lexicographic preferences. Number two is that we know a lot of work in computational social choice as well as AI and machine learning has been focused on this field, right? So a lot of you here have done a lot of work. By the way, this is by no means a complete list. I'm probably missing a lot of different interesting work that you have done on voting, on hedonic games, on matching and even kidney exchange, on assignment and housing problems, and some recent work on fair division. In AI and machine learning also, there's lots of works about preference learning, and there are some works on generalized lexicographic orders for recommendation systems. So these are works that, again, think about preferences of people over choices to be lexicographic. And the third is that when we study lexicographic preferences, we kind of learn a lot about the problem. We learn the negative results obviously carry over to the general classes, right? So as you're going to see today, I'm going to talk about a variety of negative results. So for instance, the hardness of achieving envy-freeness, and it's okay, I'm going to define it in a minute, actually extends to the additive and other general domains, right? And if we have positive results, it actually reveals some structural insights for us, right? So encourage us to push more, right, to try to kind of go further and extend our results, and also gives us some kind of good understanding of the difficult or the challenges that exist in achieving positive results. Okay, so I made these 3 points just to convince you to care about lexicographic preferences. Not that you don't care. I think at least half of people here care. So the main research question that I'm going to look at is how should we fairly allocate a mixture of goods and chores under lexicographic preferences. So let's just start with the model. So just have a very basic, simple model. We have a set of n agents and a set of m items. And of course, each agent can consider an item to be a good or a chore. So we are not really telling all the items to be good or chore. So it could be different. So for one agent, these items are goods. For some other agents, some overlapping items could be chores. An allocation is an n partition. So we want to be able to create an n partition among these agents of all the items that we have. And by the way, these are all indivisible items. The most important thing is that they should be non-overlapping. And also we want to make sure that the allocations are complete. So all of the chores and goods need to be assigned. And the agent's preferences, as we talked about, are lexicographic in this model. Okay, so how do we show lexicographic ordering? We're going to start with something we call importance ordering, right? So the importance ordering over goods and chores. Over goods only and chores only, I think it's very easy to see because it becomes a very traditional way of thinking about lexicographic preferences or linear orders over items. With mixtures, you have to kind of be a little bit more creative. And the idea here is that we're going to say that this is an importance ordering of the agents, not their preferences. In the sense that the agent wants, for instance, this agent says, it's very important for me to receive the object 1, right? It's a positive object. And subject to that, it's very important for me not to receive object 2, right? So not receiving object 2 is actually becoming a very important aspect of this lexicographic ordering. And subject to that, it's very important for me to receive object 3, right? So it's like an important ordering. So if we take this important ordering, we can actually create a total lexicographic extension that gives you the total ordering over all possible bundles. Right? So this is just kind of understanding what importance orderings are. And of course, if I put all of these together, I will get an importance profile, right? So importance profile is going to look like this for 3 different agents. For the ease of exposition, I'm going to actually make it a little bit visually more appealing, right? So from now on in the talk, you're not going to see this. You're mainly going to see this type of preferences, right? So essentially, anything that is a good, I'm going to show it for an agent. I'm going to show it with blue, and otherwise it's going to be, I don't know, that's red or pink, depending on how you see it. Okay, so let's look at the definitions. I'll start with some of the definitions. Envy-freeness is kind of a standard definition. Most of you may be familiar. We want to say that each agent should weakly prefer its own bundle to any other agent's bundle. Now, envy-freeness up to any item, we have to like slightly change this because we are dealing with mixture of goods and chores. And the way that we're changing it, essentially saying that each agent, if an agent I is envious of another agent, that envy from the agent I's perspective should be eliminated by removal of one item that this agent thinks it's a good from the envied agent's bundle, and removal of any of the chores from its own bundle. So as you can see, this is a very subjective view over goods and chores, right? So it's not about the general. So it could be that the agent is envious of an item that this agent considers as a good, but the other agents received it as a chore. So, and we can also like have this weaker notion of envy-freeness up to one item, which essentially we're going to say that there must exist one of these items, right? At least either a chore or a good, right? That the removal of it one of the bundles would eliminate envy. Okay, so for economic efficiency, we care about Pareto optimality and rank maximality. For the sake of time, I'm not going to go through the definitions. I'm going to assume all of you are familiar with Pareto optimality. Rank maximality is a little bit tricky, but we can still define it, right? It's the same extensions that we can define it for mixtures. Now, if we kind of go back and look at additive valuations, the domain of additive valuations, we know a lot about, well, we know some answers to the additive valuation. So for instance, if we're dealing with only goods, we know how to compute an EF1 allocation. We know how to compute an EF1 plus PO allocation. EFX is still an open problem. Its existence. There are some special cases where there are only 3 agents and etc. that we know the existence of EFX, but its computation is still open, and its existence for larger domain is existent. Chores are actually the main problem here, right? Because we don't know much about them. For instance, we know EF1, we know how to compute EF1, and I'm going to mention this later on, but when we want to compute EF1 plus PO, we can no longer use the same techniques that we used for goods only, right? For instance, we cannot maximize the Nash welfare. I mean, it's not very well defined in this domain, like what it actually means or entails. So there's a lot of open problems. There's a lot of push in the past few years. I've been even seeing papers like very recently working on a variety of these grounds to push it a little bit further. But this problem is generally open for chores, right? Let alone for mixtures. So there's a lot of open problems that we see. For instance, the EFX computation and existence in general. Is it like something that we don't know? Its existence with Pareto optimality similarly goes with the existence of EF1 and Pareto optimality for chores only settings and mixing. So these are open problems that I'm going to try to answer some of these, right? At least under some specific domains. Okay, so as a warm-up, I'm going to give you like one kind of result just to show you how even under lexicographic domain, the result that we get for chores and goods are different, right? And that way we can actually achieve more and understand more about the general problem. So one of the things is that we, in the chores only, so this is one of our results, we showed that in the chores only setting, even under lexicographic preferences, determining whether an allocation or an instance admits an envy-free allocation is NP complete, right? This is in contrast to the goods only setting. In goods only setting, it's actually very easy, at least in this setting, in the lexicographic setting, because you can just look at the top ranked items and that's it. And the rest of it. But for chores only, it's not the case. It becomes more complex. And this actually tells us that EF plus PO, we also show that EF plus PO is also NP complete, which as a corollary, again, it tells us that even for mixed items, this is going to be hard. So if it's hard for chores, for mixed item is hard, then again, this also tells us that this problem is going to be hard for the general class of additive valuations. So that's how we're kind of lifting the results. Now, the first main result I want to mention is the non-existence of EFX in mixed items, right? So we basically show that there exists an instance, and this is an objective instance in the sense that everybody, all the agents agree that the items are goods or chores, right? Now, in this case, I have, and we show that this instance does not admit any EFX allocation. And for this instance, we have two agents with the exact same preferences and two agents with the exact preferences in this way. There's only one good involved, and there are 6 chores. And in this case, we show that you cannot satisfy any possibility. And we do this by case analysis, right? I don't want to go into the details of it, but the idea here is that in the case analysis, we analyze that, well, if you arbitrarily give a 1 to one of the agents, then there is no other way that you can give all the other items and distribute the rest of the items among the agents such that you don't violate EFX. Everything we do at some point, we're going to violate EFX. Right. Now, one thing, I don't want to go into the details of this because it's just case analysis, but one thing I want to mention is that these results actually extend to non-monotone and additive valuations. Right? So now we know that EFX doesn't exist for even additive valuations, at least under the mixed items. An interesting thing I want to mention is that for the goods only setting, we know that EFX exists for monotone valuations if there are 4 agents and 7 goods. Now it's very interesting because in our setting, we also have 7 items and 4 agents. So one question that I was thinking about and I couldn't solve is that, is this a tight example? Is there a smaller example showing the non-existence of EFX? It's just kind of, I think it's a very fun toy problem to play with. Okay, so now in search for truth, what are the challenges, right? So we kind of learned that EFX doesn't exist. Where is this difficulty coming from, right? So we wanted to identify where this difficulty is coming from. And as a warm-up, let's look at one example, right? So this example is example that every agent, there exists at least one agent who thinks one item is a good. Their top item is a good, right? So their most important item is a good. Now, in this case, we actually show that you can satisfy, in fact, EFX plus PO, and this can be computed efficiently, right? And the key idea here is quite simple. What you need to do is to just give that good to the agent. Under lexicographic preferences, now I can give all of the chores of other agents, all of the common chores of other agents to this agent. Right? So I'll just give it to this agent. This agent is always happy because they get their top choice, right? Now, it's actually kind of easy because now I can find the next agent, the next agent who has the highest ranked item as a good, right? And I allocate that good to the agent. And then I can give all the remaining agents, for all the remaining agents, I can find their common chores and give it to this agent, right? And so on and so forth. So in this case, 5 would be the remaining common chore because the only remaining agent is this agent 3. And I give this to that agent as well. And you can continue this process, right? And as you can see, like only the last agent can receive more than one good, right? That was good for somebody else, right? And this actually gives us an interesting kind of algorithm to find an EFX plus PO. So we showed that if there exists one agent whose top item is a good, we can actually satisfy EFX, and even more than that, we can do PO under lexicographic preferences. And this also kind of tells us that we can compute the same thing if there are no common chores, right, at all. Okay, so this brings us to this kind of definition of terrible chores. So there are some, we looked at this more carefully and we figured out that, okay, so what is the issue? So if there is an agent with the top good, we can achieve this. So what is the issue? It looks like the issue is coming from what we call terrible chores. Right? And these terrible chores are essentially the chores that are really, really important for the agents not to have them. And the instances with terrible chores are the instances where every agent is in this shape. Because remember, otherwise we can't satisfy EFX plus P. Right? So we call these instances with terrible chores. And then we show that, in fact, using these instances, we show that deciding whether there exists an EFX allocation is also NP complete. So this is kind of, again, the first computational results for EFX showing the hardness of EFX, which, as you can see, it definitely carries over to the additive valuations and all the other general domains. And we also show that with PO, because our instance actually is a PO, the Pareto optimal instance, we show that it also, EFX plus PO is also hard. And note again that this problem is tractable for goods only and chores only under lexicographic preference. All right, so what are the special cases? Well, you might ask, well, okay, so now you showed the hardness. What else can we say here, right? We defined a set of instances called separable, or preferences called separable lexicographic preferences. Right? So these separable preferences, we want to kind of put them in relation to other preferences. So in one case, you have chores only. The other case, you have goods only. The separable mixed instance preferences are kind of like a generalization of those. And then you have lexicographic preferences. And then, of course, you have additive preferences. So this is the relation between them. The idea of separable preferences is that every agent is going to say that for me, all the goods are either more important than all the chores, or vice versa, all the chores are more important than all the goods. Right? So these are generally, we call them separable preferences. As you can see here, all of these agents are saying that, well, all the chores are more important than all the goods, and so on and so forth. Right? And remember, our non-existence result was the one where you have a good in the middle. And for separable preferences, we actually can show that you can actually satisfy EFX plus PO exists and can be computed in polynomial time, right? And the idea here is to kind of focus on the terrible chores, what we call terrible chores, right? In fact, in this case, we're going to focus on common terrible chores, all the terrible chores that are common with all the agents. And we can do a serial dictatorship over these agents, just give them one chore each, right, until you ran out, and the last agent obviously gets the rest of the remaining chores. Sorry, the first agent gets all the what's it called, the number of common chores minus n plus one, and then each other agent receives at most one of these terrible chores. Once we are done with this state, then we can actually we can continue as before, and the reason was that is that we know that all of the remaining items are goods for someone, right, at this point. So we can start kind of allocating as they did before, and we finish this allocation. And then in phase 2, let me see if I can see my own screen. Okay, here. And in phase 2, we can start kind of allocating all the remaining items that only this agent considers as a good. Right. I don't want to go into the details of the proof, but generally speaking, the proof of EF1 here, EFX is not very complex in this case. However, PO, Pareto optimality, is an issue. And I want to just introduce this lemma. So we have this lemma, I'm calling it PO preservation lemma. And the idea here is that if we can somehow achieve a Pareto optimal solution for the instance, for the part of instance where it does not have terrible chores or common terrible chores, then I can actually extend this by adding the terrible chores, and that will preserve Pareto optimality. Again, for the sake of time, I think I have to go a little bit quicker. So the next thing I want to talk about before talking about EF1 is maximin share, right? So again, maximin share is this idea, for those of you who are not familiar, is that you would ask each agent to basically put all the items into the bundles, right? So into n partition, and assuming that the agent is going to receive the worst one of them, right? The worst one, chooses last, for instance. And if every agent does that, then every agent has a threshold, and if we can satisfy this threshold, we can say that we have an MMS allocation, right? So under additive, so there are lots of research on MMS. I don't want to go into the details of them, but under additive valuations, there are a bunch of different results. We know that MMS doesn't exist, and there are some multiplicative or ordinal approximation. Under lexicographic preferences, the good news is that for both goods only and chores only cases, we know how to satisfy MMS. However, as it turns out, when we look at mixed items, no multiplicative or ordinal approximation of MMS exists under additive. So the question is that, well, under mixed instances and lexicographic, what can we say about this, right? And the good part here is that under lexicographic preferences, we can see that MMS is very easily characterizable. We can characterize it by the top item of each agent. So here's how it goes. If the top item of an agent is a chore, like agent 1 here, then their MMS is exactly any bundle. Their MMS, the worst bundle that they can receive, is putting this and all their goods into the same bundle. If their top item is a good, their MMS is exactly the fewer number of goods. Now there are two cases, like so, because you want to leave all these other things, so you're going to leave O1 and O4 in a partition and put all of the remaining goods into one partition, right? And of course, that is only when you have enough goods. If you don't have enough goods, your MMS is actually empty, right? So in this case, there's only 2 goods left. So your partition would be partitioning these, and then you have an empty partition. So this is just, this characterization actually helps us to kind of develop an algorithm for MMS and show its existence in the mixed items. Now, before showing its existence, I want to say that it's important to focus on the terrible chores again. And the idea there is that we show that any EFX allocation gives us MMS. So for the case of separable preferences, or when there are no common terrible chores, we can always compute an EFX plus PO, as we showed before, and achieve an MMS as well. Right? So that's also it's going to satisfy MMS plus PO. Because of that, we're going to focus on the cases where the agents have these common terrible chores. And for these cases, the way that our algorithm works is that we start with any fixed ordering, and we're going to assign the remaining items of each agent to them. So agent 1 receives all of its item. Agent 2 is going to receive an item that this agent that has left.
Hadi, I think does not remain so much time, so maybe 2 minutes left.
Oh, wow.
Fine
Okay.
with that. Sorry.
Okay. All right. So I'll try to make it a little bit quicker and just jump into it. Okay. With 2 minutes, let me see how I can handle this. All right. So I'm not going to go through the algorithm, but MMS can be satisfied. And we know that MMS plus PO can also be satisfied in this case. I want to also give you a 1 minute kind of summary of EF1 plus PO. We know that, as I mentioned, EF1 plus PO for chores is a difficult problem. It turns out that even under lexicographic preferences, this problem is very extremely challenging. So if you try a variety of techniques that we know, it's going to fail. And the idea here is that, like if you look at this instance, in this instance, for instance, we have to allocate O1 to this agent 1, even though this is not a very rank maximal allocation. The problem is that I cannot also allocate any of these items to agent 1 because that will violate Pareto optimality, because any other agent would flip with them and would prefer to have those. So actually satisfying EF1 plus PO is a very challenging problem, even in the lexicographic domain. We can actually satisfy it only if there are at least n-1 common chores. We give an algorithm about how to do that and a proof. And the idea of the proof is that we want to make sure that the first part of the we want to make sure that this part is PO, and then we use the same lemma to allocate the rest of them in the EF1 and ensuring that this PO is preserved for the rest of the allocation. Again, for the time, I'm not going to go into the details of it, but it has a very cool idea. However, we cannot do better than n-1. In fact, we even argue that even doing n-2 common terrible chores is not enough, and it becomes very challenging. So we need new techniques to solve this problem. So this is the proof. And okay, so I'm going to conclude by saying that Lexicographic preferences are important. They're challenging, as we showed that some of these negative results actually solved several of the open problems that we had, even for additive case. It's a very natural framework to think about how to solve problems and then lift the positive results to the higher. There are a bunch of open problems that I talked about in this domain that I would like to chat with any of you if you're interested. And thank you so much. And if you have any questions or some ideas, please feel free to contact me, send me an email. I'm always happy to chat.
Thanks a lot, Hadi. Let's unmute ourselves and give a round of applause for Hadi. Okay, I don't see any questions in the chat. Someone wants to ask a question to Hadi directly?
I see Dominic's hand up.
Yeah, so I have a question. In the lexicographic domain, is EF1 enough? Because EF1, you ignore the most important thing in someone else's bundle in order not to envy it anymore. That feels too much. But EFX, we've seen, cannot be done. Is there anything else in between? Maybe only defined for lexicographic or only making sense in lexicographic?
Yeah, like there is, okay, so it's a very good question you're asking. I don't think EF1 is enough, but even that, I showed that with, if you want to achieve EF1 with PO in the lexicographic domain, even that is very difficult, right? EF1 alone, you can satisfy it. You can do double round robin on there. There is this envy graph algorithm with Bhaskar et al. And they show that you can satisfy EF1, but even with PO, you cannot satisfy that for mixed items. There was this discussions that we had, and I have some notes on that we were trying to develop this another notion which was based on MMS, and it's essentially because MMS is very weak in this domain, right? As you saw, right? It's not a very weak guarantee, but we wanted to kind of define something between MMS and EFX. Essentially, imagine you are applying MMS in a recursive way, right? And you can do that because you're dealing with lexicographic preferences, right? But we don't have any positive results. Basically, what we showed at that point is this is different than EFX, and it's also different than MMS. So it's something that we need to work on it a little bit more. But yeah, I'm happy to hear any thoughts you have on any alternate fairness notion.
Other questions? Maybe I can ask one by waiting the others. In the context of additive utilities, we have the hierarchy of fairness criteria, like envy-freeness implies proportionality, which implies MMS, etc. And I was thinking whether such kind of implication relations still hold for lexicographic preferences.
Yes, it does. So we in our papers, the ones that I mentioned in the beginning, we actually give a very characterization of all of these different fairness notions. We show that which ones implies the other one and so on and so forth, right? So one of the things I mentioned is that, for instance, EFX does imply MMS, but it turns out that between EF1 and MMS, there is no relationship, right? Just like, so neither of them imply, and which is the same for additive valuations. So even like under lexicographic preferences, these two are not necessarily the same. So it doesn't give you much more. So many of those things stay here as well, right? So many of those relations. You would hope to get more relations, but it's not very obvious. Yeah.
Okay. Other questions? Okay. Rohit, so it's just a remark for Dominic.
Yes, yes. Thank you, Rohit. Right. Yeah. So we do have in the paper. I think Rohit is mentioning our paper. So in that paper, we actually think about some relaxations of EFX. So EFX, we call them EFXG and EFXC, right? So EFX where want to only remove goods or chores, and we show that the counterexamples actually hold in those cases too. Yeah.
Okay.
Thanks. I have one other question if we have time. So are there any negative results that depend on them be goods or chores not being objective, where people disagree about whether they are?
No, actually, the interesting thing is that we started thinking that the subjective aspect would make it more complex, but it is not the case. So in fact, all of our negative results, in fact, both computational and axiomatic are objective, right? So, and it's kind of, I mean, once I say it, it becomes very easy to see, and even though initially we thought about this very, very extensively, is that because you have Pareto optimality, if you care about Pareto optimality, for instance, you are forcing the goods to always be allocated as a good, right? Because you cannot allocate a good as a chore, obviously they can just exchange, right? That's just kind of like an insight, right? It's rather than an answer to your question. But yeah, like not so far. Yeah. By the way, I'm gonna be in the breakout room, so anybody wants to chat, I'm happy to chat as well.
Very interesting, really. And I was also a bit surprised by this fact, like Dominic, at the beginning, I was thinking that this objective was important, but it seems that it's not the main important point for your result to hold. And it seems to me very, but your intuition seems to be fair, yeah. Okay.
Yeah, so far we haven't found. I mean, I don't know. There might be some parts of this problem that we haven't, some angles that come into play. But
yeah.
So far, most of our results are essentially for objective instances.
Okay. Other questions? Maybe more for breakout rooms? Yeah. So maybe now coffee break with Dominic, who will assign us to different rooms for chatting. I think. Yes. So let's start again with our second speaker, who is Martin Bullinger. Martin Bullinger is a PhD student at the Technical University of Munich, and he is in the group of Felix Brandt, and I think he's at the end of his PhD, if I don't say any mistakes. And he will talk about superiority of instantaneous decisions in thin dynamic matching markets with different co-authors from also TUM, I think. And yeah, please, Martin, the stage is yours.
Yeah, hi everyone. And thanks a lot for having me. So I'm really, really happy to speak in the seminar. It's very, very exciting for me. And like Anna said, I'm really at the very end of my PhD. So I'm defending my thesis in exactly 13 days. So, but it's a very good way to have this in between presentation to, give also another presentation. So anyway, I'm talking about this paper, and this is actually also what I really like about this work is that it is joint work with 3 other very nice PhD students at TU Munich, like Anna, I guess, so Johannes Bäumler, Stefan Kober, and Donghai Zhu. And I think I've seen at least 2 of them, so Johannes and Donghai should be also in the audience and will hopefully help me answer questions if you have some during the talk. All right, so let me start talking about this topic and give you some motivation. I think so many people here in this audience have at least touched matchings, or many have also worked on matching. So and what I'm studying is dynamic matching markets. So basically the general idea is markets of dynamically arriving agents, and these agents are seeking partners. And I think they're like the matching problem is really one of the problems that has an abundance of applications. So for instance, labor markets, school choice, dating platforms, ride sharing, kidney exchange, and so on. So there is really a lot. And the central question about matching markets is always how to obtain matchings of good quality. And this is especially important in a dynamic matching markets where you basically only gather information over time, and then how do you really take a good decision? Okay, so let me give you a bit of an impression about the specific model that I will be talking about. So I think matching markets is also an area where there have been proposed really dozens of models, and many of them share some similarities, and I will try to give you the general ideas and then the exact specifications of our model. So we are considering a continuous time model. And during this time, we always have an active matching market. So here, for instance, we have these agents A, B, C, D, and E. And then as time proceeds, at some point, there might be an agent, a new agent arriving. Okay, so this might be this agent F, and one specific part of our model is already that we stochastically decide on the compatibility of agents. So for instance, we have a parameter P, a probability of each edge to form, and then we can throw these biased coins, and for instance, then we have compatibility of agent AF and agent FD. And now this agent F will have a certain sojourn in the market according to a departure distribution, and also this departure distribution is a random variable. So every agent is endowed with a random variable which decides how long this agent will stay. Okay, and now as time proceeds, maybe at some point, so this is now not a feature of the market, but an algorithmic decision is to match some of the agents, and then if some agents are matched, they can leave the market. So this is something that might happen to our market, or there might be a new agent arriving and forming edges, again, according to a probability distribution, and this might lead to a new matching opportunity for our agent F. And then at some point, when we reach the final time in the sojourn of agent F, then agent F has to perish. So if agent F is not matched until this, so this is the very last point in time where it can match, and after otherwise agent F will just perish from the market. Okay, so this is the life of an agent in the matching market, and basically this happens then with a lot of agents in this market. Okay, so let me be a little bit more specific after this picturesque introduction. So we have agent arrivals according to a Poisson distribution with rate m, and then like I said, and like you've seen already, then we have the compatibility of agents with respect to these independent biased coin flips, and the key feature of our work is this departure distribution. So we have a departure with respect to some distribution, and this sum distribution will play the key role in our results. So what happens under various distributions? And this model is basically based on two previous works by Akbarpo et al. In JPE, and by Anderson et al. Published in OR. Okay, and again, let me repeat the central question. So how to match the agents? So what is a good algorithm to match agents, and how also to measure the performance of the market? So this is basically things we should, so the latter one, so the measure of performance is something that we should agree on, and how to match agents is what we really want to find out. Okay, so let's look at this market again, and let's talk about two important matching algorithms that we are looking at in our work. So the first one, whenever an agent arrives, the first algorithm will match the agent right away. And this is the so-called greedy algorithm. So whenever we can take any matching decision, then we also will take the matching decision. So the sojourn does only play a minor role, because within the market, so once we have this matching, the market will always be empty. So we never can, unless an agent arrives, we never can take a matching decision in the market. So there is the only possibility to perish is that you stay in the market and you're just not matched when a new agent arrives. Okay, so this is a greedy approach, but maybe so in a lot of work, greedy approach might also not be the best decision. But in this work, we'll show that these instantaneous decisions taken by greedy can actually be pretty good under some conditions. Okay, so a new agent arrives, and okay, so a second approach is, now that we have this market, and in this market we already have some, so in the second algorithm type, we already have some edges present, and then when a new agent arrives, we just do nothing. We wait, and we just want to make the network grow. We want to make the market grow, and we want to increase our opportunities of matching. And now we can define an algorithm which is called a patient algorithm, which waits until the last point that we can match an agent. And only if this happens, so if we get the information, now this agent D, for instance, is being critical because agent D is about to perish, only at this point, we are going to match D with one of the neighbors, say uniformly at random. Okay, so this algorithm, or this class of algorithms, I mean, they're still the type breaking, can play a role, is called patient algorithm. Okay, and one important difference here is that we can only use this algorithm if we really have the information about when an agent is going to perish. So if the matchmaker really has this information, then we can use this algorithm. Okay, so these are the two main algorithms. And now the second question, so these are the two main algorithms I want to look at. And now the key question here is how to define the quality of our algorithm. And the primary goal that we use here, and also here different goals have been considered, is to minimize the loss of agents. So we just treat all the agents equally. There are no weights or something like this. And our goal is to minimize the asymptotic loss, so the expected fraction of perishing agents. And this is defined as the following quantity. So we take the expectation of the lost agents. So basically, this is the new arrivals. Then some agents leave because of being matched. Some agents are still in the market at some point, capital T, and everything else is what we have lost. And then we divide this expected number of lost agents and compare it to the expected total arrivals. And then we take the lim sub for the arrival rate and the time horizon T. And so one important feature here is that if we just now increase, so if we take this limit and let m and t run to infinity, then somehow if we don't control the density of the network, then the network will just be very dense, and this will facilitate matching decisions, so matchings of good quality. Therefore, we want to retain a sparse market, and therefore we say the markets should always be of the same density. So if we increase m, then d has to be constant, so the matching probability has to converge to 0. So if the matching probability eventually will be very, very small if we have a high arrival rate. Okay, so we are operating in a sparse market, and we are now, the question is, what is a good matching algorithm with respect to loss? Okay, and before I present to the main result here is, let's briefly discuss these algorithms. So I think greedy is a very, very natural algorithm and very frequently used in practice. So it's very easy to understand and to implement. And one advantage of greedy is definitely that it avoids long waiting times. So this patient algorithm really keeps agents in the market as long as we can. And the patient algorithm, by contrast, as I already have said, needs information. And one other approach, so I would say also greedy and patient algorithm are not the only algorithms, but for instance, also one thing that is considered are batching algorithms, where we just wait for some time and then we make several matching decisions simultaneously to clear the market as much as we can. And the general paradigm in dynamic matching markets, I would say so, this is a reoccurring theme that I've seen in a lot of papers, is that what really facilitates the good performance of algorithms independently of how the matching decisions are done is, if we want to have a good performance, we usually need a thick market. So we need a large number of possibilities to take our decisions from, and then we can have a good performance. And this is promoted by a lot of recent work and basically all of the domains that I've said. So adoption markets, for instance, work markets or kidney exchange markets here. So and by a lot of paper, this paradigm is promoted. And also, whenever, so greedy algorithms are really a type of algorithm that are very natural and often considered. And also, the standard paper on a greedy algorithm is the following: the authors define a certain setting, and then they find conditions under which, in their setting, the market is thick, and then they prove that the greedy algorithm performs well. So whenever greedy type algorithms are considered, then if they are to perform well, then this is usually done in the thick market. And the papers I cited here are some examples of this paradigm. Okay, so what we will eventually do, and this is also in the title of the talk, is we will show that the greedy algorithm can also perform well if you're in a thin market. And so just to give you some motivation why this is highly interesting, is that thick markets also have some disadvantages. So they can cause congestion, which basically means that there are too many agents and then too many decisions to be taken, and we don't, it's hard to elicit what are the good decisions. And this is actually backed up also by real life data. So for instance, by these two works where either the size of outcomes or the quality of outcomes can be bad because of market congestion. And also the obtaining departure information can be very costly or unethical. So we don't really know if it's even practical to use algorithms like the patient algorithm. Okay, and the goal, and we will be able to achieve this goal, is the best of all worlds. So basically, we don't want to have any information because we use a greedy algorithm, but so we want to have a good quality of the outcome. We want to do it in a thin market, and basically because this will be achieved by a greedy type algorithm, we will also get low waiting times. So the first and the last one of these bullet points are achieved because we use a greedy algorithm, but what we really have to work for is to prove that it works in a thin market and that this achieves a good quality. Okay, so our benchmark is a theorem by this paper by Pareto et al., which I already cited when introducing the model. And what these authors prove is that the departure time, if the departure time is exponentially distributed, then the loss of the greedy algorithm is somewhat large in the sense that it's inverse linear, and the loss of the patient algorithm is exponentially small. So basically, if you want to summarize this in one sentence, is the patient algorithm outperforms the greedy algorithm. And the reason for this really is this exponential distribution of the departure time. So that's why I said this is the flexible part of our model, and we will really show you how this result breaks down if we use some other departure time, or how we can complement this result. Okay, so our main result is that if the departure times are distributed according to a probability measure, which basically does not have density around zero. So let's assume, for instance, agents are not allowed to depart from the market between the time they arrive until 1 unit of time is over, then the loss of the greedy algorithm is also exponentially small. So there are some other constants here in this exponent, but basically this is exponentially small. Okay, and basically typically one case, the typical case of this theorem is the case of unit waiting time. So every agent waits in the market for exactly 1 time unit, but it extends also to basically every other model if you have an arbitrary lower bound on the maximum waiting time. So it doesn't really matter if this is 1 time unit. Basically, we can reformulate this theorem by having an epsilon amount of time where every agent is guaranteed to be in the market, and then this constant here in the exponent changes, but it's still exponentially small waiting time. And what's also important to note is that the performance of these algorithms is close to the optimal performance. So what we can also prove is that any algorithm has to have a loss. So under a very, very general, so for instance, here, this is for the unit waiting time, this is the constant for the unit waiting time, but basically for more or less all reasonable departure distributions, the loss has to be at least exponentially large. Okay, so the greedy algorithm performs already well. The greedy algorithm performs well with respect to the loss. The greedy algorithm doesn't need information. The greedy algorithm has low waiting times, which I will show next. And because it always takes decisions right away, it operates in a thin market. So it does exactly what I promised. Okay, and maybe let's quickly compare. So why does it work for unit waiting times and why doesn't it work for exponential waiting times? So this is probably the natural question. And basically the high loss of the exponentially distributed, but also for others, so for other distributions where we find the high loss is always caused that departures can basically be performed instantaneously. So agents come and depart right away, so they don't even have a chance to match. If they don't have a matching right away, they don't have any chance to match. And this is because the exponential distribution has a high density around 0. So basically, to say why it works, then in our cases, we have a more evenly distributed Saussure. We have the same expected Saussure time as, for instance, the exponential distribution, but the times when we depart are more evenly distributed. Okay, so let me also quickly talk about waiting times. I think that the more exciting result is about the loss, but why do we have small waiting times? So this is a proposition which resembles also of Little's law. So we can measure the waiting time, the total waiting time as an integral of the pool size And then basically we get a bound on the total waiting time by bounding the pool size. And as I said, the pool size is quite small, so we also have small total waiting time. And again, this is something where we can prove this is optimal up to a constant. And for this result, this constant somehow depends also on the departure distribution. But basically, again, if agents are allowed to leave the market at time 0 when they arrive, then of course, so if we have very, very, very high density around 0, then of course we have a very, very low waiting time because agents just come and go, but this is not very unreasonable. So for every reasonable departure distribution, we have a waiting time that matches this upper bound. Okay, and again, under algorithms like the patient algorithm, we have, of course, very long waiting time. So this is constant compared to, so we don't have this 1 divided by d factor here anymore. Okay, let me conclude with one more interesting observation, which I found actually very interesting here, is that we also did some simulations and evaluated the greedy and the patient algorithm. And one thing that I found very, very interesting, but which we cannot explain theoretically, is that the loss of the greedy algorithm and the patient algorithm seems to be somewhat identical. So here the blue crosses is the loss of the patient algorithm. Here you can see the density parameter, how this evolves, and here you can see the loss. And basically this seems to be somewhat identical. And here also the red lines are the upper bounds and lower bounds that we have for the greedy algorithm. So this is the corridor where the greedy algorithm has to be, and this is the general lower bound. So this is where the lower bound for any algorithm. And this is something which we really would like to explain, but where we fail to explain it exactly. We have some intuition why this should work, but we don't have a rigorous proof for this. And I think this is also very, very interesting open direction. Okay, so this is something I already said. So let me conclude. I think the take-home message of this talk is that it's really this contrast to previous literature, that we have a thin market setting where greedy performs close to optimal. So this is I think what is the most spectacular about this result. And what's then a side effect of using the greedy algorithm is that we can simultaneously circumvent congestion, information collection, and a trade-off of quality and waiting time. So usually either you get good quality or you would get good waiting time, dependent on whether you match more patient or more greedy, but we can really circumvent it here. And so I think there are many future directions of this result, and I think it's really a new perspective. So one is analyze extensions to other thin markets. So is our result now robust? So I said this in the market by Akbarko et al. It really depends a lot on the departure distribution, but what about other thin markets? So can we repeat this result somehow under some conditions, which would be, I think, also highly relevant for applications where we where it's just very nice if we have a foundation to really have a theoretical argument by matching greedy is just good. And then searching a deep connection of greedy and patient algorithm under unit departure times. So this empirical observation that we have, if somebody comes up with a rigorous proof, we have tried a lot, and I would be very curious about this. All right, that's it from my side, and thanks all for listening, and I'm very, very happy to answer any questions or hear any comments.
Thanks a lot, Martin. Let's give a round of applause for Martin. Okay, thank you. There are some questions in the chat. Maybe the persons who ask the question want to directly ask them. Judy, for instance.
So my question, I think, is the same as Sanj Gupta's, which is, were you assuming anything about the departure distribution here?
Yeah, so in this experiment, right, in the simulation. Yeah, so here the assumption is unit departure. So we assume that agents stay for exactly one time unit. And that's also why we thought maybe we find a connection, because so something like time reversal or something that we see that basically matching at the last possible point and the first possible point should be somewhat similar, but the pool sizes are very different here. So we don't have a clear mapping of these two algorithms. Or
Okay.
or does this answer the question?
Yes, thank you.
Bill also has a question, but I think it has been answered by Johannes. Bill, are you satisfied by the answer, or maybe?
No, I just wanted to make a comment. It doesn't seem reasonable that a person who's on the market for an extremely short time would expect as good a result as someone who's on the market longer, and that might even serve an incentive purpose. So it seems to me that it makes sense to consider it a weighted goal in which you don't punish the goal as much when agent is lost because they were on the market for a short time.
Yeah, I think actually all the agents, or I mean the agents that we lose in a greedy approach, they already stay in the market quite long. So yeah, so I think, yeah, it's an interesting idea, but I don't think that it would change a lot, because so
I thought of it as an alternative to bounding the wait time from 0.
Yeah, okay. Yeah, I see what you mean. Yeah, so maybe this might be an alternative way to deal with this high loss of greedy under the exponential distribution. Yeah, that makes sense. Yeah, thanks for the comment.
I wanted to comment on what Bill was asking. This was my question too. But what I remember is that the paper that you referred from Akbarpour et al., and they were looking at this in the context of kidney matching, I think, if I'm not mistaken. And in that context, you have patients, right? So they're waiting to get kidneys. So the wait times are really the wait times that they can tolerate. Of course, their health can kind of go bad. I mean, it just kind of, but it can degrade, right? But it's really not about the time that they can decide by themselves how much they want to. So it's more part of the input to the problem. If I'm mistaken, Martin, what are your thoughts?
Yeah, so I think if you particularly think about a kidney exchange market where agents don't really have an incentive to leave the market because it makes no sense, they really need a kidney. So then their departure distribution would be that they stay for a very long time. But I think still it would be good in this case, I think in the case of kidney exchange, to have a pure loss objective is not very reasonable because waiting times really make a difference. So, and if you use the patient algorithm, you're pretty good with respect to loss, but you're extremely bad with respect to waiting times. So, and I think our work gives a justification to use greedy type algorithms if you're in a setting like the one we defined. So if we are in the setting by Akbarpour et al., and if we agree that this models kidney exchange markets well, then this work gives justification to just match when we can.
By talking about algorithms, there was a question by Peter, and also I had the same in mind. Do there exist some intermediate algorithms?
Yes, what I have in mind is the greedy algorithm. As soon as you have an edge, you remove it. But you could wait for the edges to arrive up to some density threshold where the chance is enhanced that you can remove multiple edges. In your example, you had, it was actually the case that the moment when this node F arrived, a perfect matching was possible, which wasn't possible before. So then you could empty the entire market. So rather than immediately acting or waiting up to the point that someone is leaving, can you use some kind of threshold with the density, deciding when to act?
Yeah, so we have also thought about can other algorithms perform better? And I think I have two comments for this. So one is that we have this lower bound for any algorithm. So basically, here this lower bound basically tells us that maybe we can do a little bit better with an arbitrary algorithm, but there's really not much space to be a lot better with respect to quality. And I think we have this matching lower bound for both greedy and patient. But yeah, so basically the question, and this is the question that's behind your question, is really, can we say something about the truly optimal algorithm? So even for the greedy algorithm, something that we did not exploit at all is the tie breaking for the decision that we take. So, and the greedy algorithm can never exploit any network structure. So, and probably if you define very carefully algorithms, then you can find something that outperforms greedy by a bit, but the space is really very little. So it's you might be able to be a little bit better than greedy, but and also if you want to design algorithms where you weight and you don't have access to the departure attribution so to the exact departure information. So if you don't really know when an agent gets critical, then it will probably be very hard to beat greedy, because you will also lose more agents because of them perishing. If you have access to departure distribution, for instance, if you know that agents will stay for exactly 1 unit time, then, for instance, we also analyzed the patient algorithm for unit times. Then, and this also has an exponentially small loss, which is not really a great surprise for us. But then maybe you can define something that for sure outperforms greedy in some instances and never performs any worse. But like I said, there's very, very little space to the optimal performance of an algorithm.
Good, thanks.
Thank you. There is another question by Sanjutta. Maybe you want to ask it?
Yes, my question was that the optimal bound that you have, does this bound depend on the departure distribution?
You mean this bound here?
No, the optimal close to this LL.
This one? Yeah, so basically, I depicted the optimal performance. So it depends somewhat, yes, it does depends on the departure distribution. For instance, it depends on the expected value of so if the agents have a similar departure distribution, but the expected value for some is just a lot larger than the others, then it makes a difference. So we have a more general statement in our paper where it's basically phrased with respect to the expected value of the departure distribution. But yeah, so
still the gap is very small between greedy and
but the difference is always just a constant here. So there might be some. So if agents in expectation stay longer, then this constant here will be a lot. Might be larger. So here the expectation also occurs, and then since we have this exponentially small thing, then this will be even smaller. Yeah, but the magnitude, like this exponential magnitude, stays the same.
Yeah, thanks.
Other questions? Maybe I will have a last one, which is very naive. You were talking about compatibility for the matching of the agents. Does it make sense to assume more, not necessarily the preferences, but something which can be 0, 1 more compatible, or 0.5, you know, something like that, which would be intermediate in the measure of compatibility?
Yeah, I think we tried to get more general compatibility models. So first of all, so I think the analysis gets a lot harder, and our analysis depends on really this Erdős-Rényi type of graph that we create over time. So yeah, I'm not sure how robust our result is if we really consider a more general compatibility models, but it definitely makes a difference. So some of the related work where I said that thickness makes really a difference is you can also, instead of having compatibility or non-compatibility, you could also say you have a weighted graph, and the weight tells you compatibility, and every pair of agents is compatible, and then you compare the maximum weight with the and then it depends very, very much on it depends on the weights. Yeah, so if you have a very dense market, then again you can perform well, and you have a dense market if M increases, so then you probably need something like our density parameter to scale down the high weight, to have small high weight possibilities. But yeah, so it's not really clear for me how to do it in an easy way.
Okay. Thanks. Judy, you had a last remark?
I was just thinking about wait times and how some in the kidney market, there are very different distributions. There are those people who, the cadaver donors that don't last. And there are people waiting for kidneys who can be there for quite a long time. So I'm thinking there may be more than one distribution you want to look at.
So you
make the analysis much harder.
You mean, for instance, what happens if the departure distribution of the agents is not identical?
Right.
Yeah. So so I think both for definitely for the loss, basically we also can allow for the loss we definitely also can allow different departure distributions for the agents, so the result doesn't break down, as long as we have this guaranteed Saussure in the market. So basically, whether some agents might stay indefinitely in the market and some leave at time 1 doesn't make a difference for our result. So agents can have within the framework of this condition that everybody has to stay for a guaranteed amount of time, we have some flexibility in the result. And like I said, you can push this arbitrarily small, but if you make it very, very small, then like the constant in the exponent will grow, and then the loss will be larger. So the loss bound will be larger. But yeah.
Okay, thank you.
Okay, maybe we will close the seminar now. Thanks again to our speakers. Okay, thank you to all of you for attending. And I think we will meet again remotely on the 12th of May, if everything is going well. And anyway, we will announce the details very soon by the mailing list, like usual. Thanks a lot to all of you, and have a good afternoon or evening, depending on the hour in your country. Bye.